So, welcome everyone to another Math Club talk. Today's talk is on percolation theory by Ishaan Bhadoo of BMath third year. His interests lie broadly in probability theory and parts of geometric group theory. And so, over to you.
Right, it should be working. So thanks everyone for coming. So today I'm going to talk about percolation theory, and the main result that I want to prove by the end of the talk is that critical percolation on exponential growth graphs dies. So I'll explain what all of that means. So first, let me start by introducing the model. Okay, yeah. So basically, you start with the infinite graph, and for each of the edges, you are tossing a coin. It's a biased coin, and you're tossing it, and if you get heads, you're keeping that edge, and if you get tails, you're removing that edge. So that is the process, and after you do this, you will get some random subgraph of the graph G. And so this model was first introduced by Broadbent and Hammersley in 1956 in their paper titled Percolation Processes, and so it's been very widely studied nowadays. So this is just some illustration. So as you can see, this is a graph, so Z2 or something, and we are the different colors represent the different connected components of the graph, and you're removing some edges, you're keeping some edges. So you can imagine that you're pumping water into one of these things, and the water can percolate. That's the same cluster. So if you're pumping water in this green cluster, everything in the green cluster will be reached. So different values of p will give you different random subgraphs. So if you have a higher value of p, you will tend to cover the entire lattice. If you have a lower value of p, you will have a lot of closed edges. Okay. So what we want to study is the connectivity properties of the random subgraphs that we get after doing percolation. Like, are they connected? What are the distributions of the connected components, and how many infinite clusters are there, and so on and so forth. So for that, we first define this theta p. So you fix a vertex, say the origin. Let's say for the moment we are only working with z2, and you fix the origin, and you define this function theta p, which is the probability that the origin is connected to infinity. What that means is that if you do the percolation on z2, the probability that origin is in an infinite cluster, and we want to consider this critical value, which is the supremum of all value of p, so that theta p is 0. So when you start at 0 with probability 1, you will have no 0 cannot be in an infinite cluster because all the edges will be closed. As you increase the value of p, there will eventually come a point where this theta p will be positive. So that point is the PC. So after that point, with positive probability, the origin is in the infinite cluster. Okay. So one natural question is that, is this a monotone event? Like in theory, you can switch back and forth between having 0 in an infinite cluster and not, but you can use something known as uniform coupling of the percolation model to show that this PC will, like after you hit theta p equals to positive, then you will stay. So theta p is in fact an increasing function. Okay. So there is typically a phase transition. So first I want to say what I mean by a phase transition. So imagine a large system, and if you're doing small perturbations in the system, and that leads to a big change in the entire system. That's what a phase transition is. And so here the perturbations are changing making the edges open and closed. So as you increase the value of p, you're making these small changes by making some edges open. And the question is that, is there a phase transition? So is there a value of p strictly between 0 and 1, after which you, with positive probability, there is a origin, the origin is in an infinite cluster, and before that it's not. So typically in this sort of percolation models, we see a phase transition, and PC will be positive for all graphs with bounded geometry. So if the degrees of the vertices are bounded by some number, then we can show that PC will be positive, and PC will be less than 1 also for all graphs except the trivial cases where the graph has linear growth. So except Z, essentially except Z, everywhere else we will see a phase transition. So this is just one thing, that if you have a graph with superlinear growth, so if you're considering fixing a point x and you're looking at the ball of the radius r, and you're looking at this limit. If this limit is infinity, then you call it superlinear growth. So for example, z is not superlinear growth. This limit will be 2, and so graphs with superlinear growth will have a phase transition. So this was recently proven in 2020, and they also proved in the same paper that PC will be equal to 1 if and only if G has linear growth. So essentially what this says is that only for Z will you not have a phase transition. Everywhere else you will have a phase transition. Okay. So one of the big questions is what is PC for a general graph? And we know the answer for trees essentially. And for a D-regular tree, we know that PC of TD is equal to 1 over D minus 1. So I won't be able to prove it in complete generality, but I'll show one inequality in the lecture later. And for Z2 also we know that PC of Z2 is equal to half. But I mean this might give you a wrong impression about the theory, because in general we do not know anything about the value of PC for any arbitrary graph. So for example, PC of ZD will be between 0 and half just because PC of Z2 is half, but the exact value is not known. We don't know if it's a nice number, if it's an algebraic number or whatever. So the values are not known. So there are two questions that you can ask. You can ask after, so I just talked about a point after which we get an infinite cluster. Imagine you're increasing the value of P beyond PC as well. So after a point, the graphs, the two different infinite clusters, the edges between them will also have high probability of being connected. So these two infinite clusters will in fact become one. So you can ask after what points do all infinite clusters connect to give one big infinite cluster, and after what point do we get a unique infinite cluster? That's one of the questions that you can ask. And how do these two phase transitions compare to each other? So we have this PC after which you get an infinite cluster, and we have this another value after which you get only one infinite cluster. What is the relation between these two? And one question that I would like to add here is, what is the nature of such a phase transition? So you can think of it like, is it an abrupt change or is it like a continuous change? When you go from less than PC to greater than PC, what happens at exactly PC? So that's, well, you want to know those answers as well. So to answer these two questions, we first set up a nice definition. We define this another threshold PU, which is the infimum of all values P, such that there exists a unique infinite cluster with probability 1. So what that means is that this PU is beyond, as after PC, so you're increasing with the value of P from here to here, and it's the smallest value after which with probability 1 you get a unique infinite cluster. So this is PU. Again, in theory it can switch back and forth, right? It can be infinity 1, and in fact that does happen for some non-transitive graphs, but we'll see that it doesn't happen for. So yeah, n infinity is a number of infinite clusters. Yeah, this diagram I'll come back to it later, I guess. So what is the first question? After what point do we get a unique infinite cluster? The first question is just asking, what is this value of, what is this PU, right? And the second question is, what is PC, when is PC equal to PU? So we want to answer these two questions, so we've changed this into some mathematical tangible sort of thing. Okay, so in general these questions are very hard to deal with and we don't even know the answer. So like I said, the number of clusters can go from infinity 1 again and again, and it's a mess. But we want to restrict ourselves to a nice case of transitive graphs. So we'll only deal with transitive graphs. So I'll just define it. And transitive graphs just means that if you have any two vertices there, the graph looks like the same from all the vertices basically. So if you have two vertices u and v, there's an automorphism of a graph G which takes u to v. So an automorphism just means that a map which preserves a bijection which preserves the adjacency relations. And okay, so that's an automorphism. So here is a theorem by Newman and Shulman that I'll prove later, that if you have a transitive connected graph, then this n infinity, this random variable n infinity, can only take these three values. So it cannot be 5. The number of infinite clusters cannot be 5 or 4 or whatever. So the fact that n infinity is constant is trivial to see, right? I mean, because n infinity is constant just because of Kolmogorov's 0-1 law, and so it is a constant almost surely. But what constant is it? Is you can figure it out, and it happens to be only 0 and 1 and infinity. So this is only for transitive, by the way. So this theorem by Hagstrom, Perez and Schonman in 1999, this also tells us that this back and forth shifting of infinity and 1 cannot happen. So if you have a transitive connected graph, then the number of infinite clusters after pu will be always 1. So after you hit this threshold, you cannot go back to infinity. That is what it means. So this definition also, this theorem will also give us an alternate definition for pu, which might seem more sort of logical to some people. Like it's the maximum value of p after which the number of infinite clusters being non-unique is equal to 1. So what that means is that you're coming from this side, and this is the maximum value of p such that before that all of you have the number of the number of clusters is equal to greater than 1. Okay. Actually, I should write not equal to 1, but okay. So these are some results, and so before I go forward, I just want to talk about, yeah. So back to these two questions. We want to ask what pu is and when is pc equal to pu. So I'll deal mostly with the second question. First question also, there are some bounds, and there is this open conjecture that pu will be less than 1 for all graphs with one end. So I'm not going to be talking about that, but I'm going to be talking about when pc is equal to pu. So the first model of percolation was studied on Euclidean lattices on ZD, and Eisenman and Newman, they proved for ZD that PC will be equal to PU. So they answered this question for ZD. But then people later discovered that the same proof in fact works for graphs which are amenable. So what is an amenable graph? So the amenable graph is so first I define the isoperimetric constant of a graph G, which is just going to be the size of the boundary of a finite set by the volume of the set. So boundary is just the points outside of the set which are connected to some points inside. So okay, so this is not for the camera, but I'll just write the del S. Is that fine, right? So set of all points outside of S which are connected to some point inside. So this is the boundary of a finite set, and we look at this constant phi g, and we call a graph amenable if this expansion constant is 0, and non-amenable if it's positive. So you can think of non-amenable graph as sort of expander graphs, and like the boundary and the volume, they're sort of comparable to each other, so the graphs sort of expand. So like a prototypical example is like a tree. So with trees you have non-amenability, and a group is called amenable if all of its Cayley graphs are amenable. So in fact, if one of the Cayley graphs is amenable, you can show that all of it will also be amenable. But yeah, I'm just saying this definition. So this is what an amenable graph is. So examples of amenable graphs are lattice-like graphs. Amenable are like lattice-like graphs. So something like ZD will be amenable. Something like the triangular lattice will be amenable, and the honeycomb lattice, whatever. The lattices will mostly be amenable. So this is the second question for these sort of graphs. That for amenable graph, there is no phase where there are infinitely many infinite clusters. So PC will be PC will be equal to PU for all these amenable graphs. So yeah, I want you to understand this. This is a very big theorem. It's a classical theorem in percolation theory, that for amenable graphs there is no phase like this. There is no phase like this. So this is sort of 1. So you just go from 0 to 1, and that's it. And the proof, I can tell you the idea of the proof. It's a very simple proof. It was refined a lot of time. So the idea is that if you assume that PC is not equal to PU, then you will get some value of P where there are infinitely many infinite clusters, right? And why is that? Because Newman and Shulman tells us that the number of infinite clusters can be either 0, 1 or infinity. So if you are saying that it's not 1, then it has to be infinity because we are beyond PC. So the number of infinite clusters is infinity, and using those infinitely many infinite clusters, you can construct what are known as trifurcation points. So points which look like these points. So if you remove the edges here, then you get 3 infinite clusters. So those sort of points are known as trifurcation points, and you can show that the probability of a point being a trifurcation point is positive for if you assume the assumption. And then if because of transitivity, the probability of any point being a trifurcation point has the same probability, and it's a positive probability. So then just by linearity of expectation, if you consider the finite set K, the number of trifurcation points will be just the sum of indicators, right? and so the expected number of trifurcation points scales with the volume of the box. So it will be some probability times the mod k if k is a finite set. But then it's a combinatorial fact that the number of trifurcation point cannot exceed the boundary. So therefore the boundary to the volume ratio will be greater than some positive constant c, which will contradict the amenability of the graph. So that's like a brief overview of the theorem. So this shows the Wodenkian argument for amenable graphs. So any questions? I mean, it's a bit too much, right? Okay. So then after this theorem, you can ask that for what other graphs is PC equal to PU. And this is a big conjecture by Benjamin and Stam in their paper that I mentioned in my abstract, Percolation beyond ZD, many questions and few answers. And so this conjecture just says that this precisely only happens for graphs which are amenable, which are well behaved. The boundary doesn't go crazy and expands. So only for PC equal to PU only happens for these sort of graphs. So there are many results which work towards this conjecture. So for a regular tree, we know that it's non amenable, and PU will be equal to 1 and PC will be equal to 1 over T minus 1. So it will never be, they will never be equal. So for these sort of non-amenable graphs, we know the answer. The first paper for this result was published by Grimmett and Newman in 1990, where they showed that for this infinity plus one dimension, also this sort of thing happens. And in fact, this is a big paper by Lally, Benjamini, and Stam that they showed it for all planar transitive graphs. So for any planar transitive non-amenable graphs, PC will be less than PU. So planar just means that if you draw the graph and you can draw it without intersecting the edges on a plane. Okay. So I mean, right now that's all I want to talk about. I don't want to go into hyperbolic graphs, but I would like to just say one more thing, that there has been this very new advance in the towards this conjecture, where Tom Hutzloff actually proved the conjecture with the additional assumption of hyperbolicity. So I don't want to go into the definition, but he established the Benjamini-Stam conjecture under this additional condition. So he's proven this for hyperbolic non-amenable graphs that PC will be less than PU as well. So for this big class, you've shown it, and so yeah, that's all. This is the theorem that I wanted to talk about, and so that's it for the slides. That's all I want to talk about with the slides. So I'll go right. So you can remove the slides. Hyperbolic graphs, I don't want to go into definition, but they're like tree-like graphs. So, okay, so I talked about what percolation is. I hope you guys understood the definition and all. So let me just start by redefining some functions. So not this, theta p. This is theta p, and PC was defined as the supremum and we had another so we had these two values, these two threshold PC and PU. And so the questions were, I was just going to write the questions here. So the first question was, is when does this happen? The second question was that what is the value of PC and PU in general? And third value is what is the nature of the transition. So writing that, I can just say so this function theta p, this is the probability that the origin stays in an infinite cluster. I want to talk about the third question the most. We want to ask what happens at PC. So at PC anything can happen. We don't know. We just said that before PC it's not there and after PC it is there. We don't know if at PC origin is in an infinite cluster. So when is theta PC equal to 0? That's conjecture. Okay, so first I'll just talk about some, right. Yeah, PU is a, yeah. So let me just draw this. I don't know where to draw it. Let's just draw it here. So PU is the point after which you get a unique infinite cluster. So the number of infinite clusters here is 1. It's infinity here and it's 0 here. So here I have written that it's the minimum value of P after which there exists an infinite cluster is equal to 1. So you can imagine that you're sitting at 1. If you're sitting at 1, then the number of infinite cluster, there will be only 1, right? Because everything is connected. And now you're going back, going back, going back. The point after which you this probability becomes less than 1 is the point after this P. Okay. So I hope that's clear. So for trees, we've answered all of the 3 questions. And so I'm going to answer each of them. And the first question is that when is PC equal to PU? So I'm only going to be dealing with regular trees because transitivity is a is a very important assumption. So we only want to deal with regular trees. So this is a deregular tree. And let's also assume that it's not like Z and D is bigger than equal to 3. So for regular trees, we know that this critical value is 1 over D minus 1. And so, in fact, this is true for D equal to 2 as well. So this will immediately tell us that PC of Z is equal to 1. But PC of Z is equal to 1 is quite obvious, right? I mean, you need all of the edges, and so PC of Z will be equal to 1. So let me just give the proof of this. So proof. So first I'll show that this is equal greater than equal to 1 over D minus 1. So you can imagine that you have a root, this thing, and you have some like this, and so this is the 0th generation, the first generation, the second generation, and we have the nth generation like this. Okay. So I want to define this random variable. So xn is equal to, so del n is a number of points which are exactly at a distance n from the origin. So points here, and so xn is a random variable because k0 is a random set. So xn will be the size of this random set. So yeah. So what should happen if c0 is infinity? So xn should be all bigger than equal to 1 if c0 is infinity, k0 is infinity. Sorry. Right, because if 0 is connected to infinity, there must be points at every level in the cluster. So then theta p is just going to be the probability. So this probability is less than equal to, right? So this is okay, just because if there is omega where this is infinite, then that omega will also have xn of omega being greater than 0. So this just by Markov's inequality is less than equal to that. Now, but what is xn? How many? So if we assume that it's d minus, if the degree is d, how many vertices will be at level n? So it will be the summation of all x belong to del n. The indicator that, right? This will be what xn is, and the size of del n will be d into d minus 1 to the power n minus 1. Right, so this is clear, right? because you have d and then d minus 1, d minus 1, so on. So if you look at the expectation, so maybe I should, I don't know, I can write it here, I guess. So the expectation of xn will be what? So all these probabilities will be the same. So what is the probability of vertex here being connected all the way to to 0? So let's just take this vertex at level 2. If this vertex is connected to 0, then this edge and this edge must both be open, right? So the probability of this vertex being connected to 0 is just simply p square. So the vertices being connected here will be p to the n. So all of these probabilities will be just p to the n. So expectation of xn will just be d times this, right? So transitivity of the tree I'm using just simply also to find the number of vertices at level n. Here I'm using that there is only one path to go to a vertex. Yeah, it's independent of them all just because percolation is an independent process. So I'm using transitivity just because that otherwise we won't get something like d. So this entire proof will work if you let d be the maximum degree, right? Because if you let d be the maximum degree, then these upper bounds will still hold. So in fact we can prove that this will be greater than or equal to 1 over the maximum degree minus 1. But in this probability I'm using that there is only one path. I'm using the treeness here, because if there were more than one path then you have to do some other things, but if there is exactly one path, that entire path must be open, and so it's p to the n. So yeah, but then what is theta p? So we just showed that theta p is less than or equal to d into for all. So what that means is that theta p will go to 0 as n goes to infinity for all p less than d minus 1, right? Just because it will be less than 1 and so it will go to 0. So for all p less than or equal to d minus 1, the probability is 0. So PC being the supremum of this set must be bigger than or equal to d minus 1. So this proves that PC is bigger than or equal to d minus 1. There's a tester. Right, so is the proof clear? Right. So we've only shown that PC is bigger than or equal to 1 over d minus 1, and in fact, like you said, that you can also show that it's bigger than or equal to delta minus 1, where delta is a maximum degree by the same argument. I have not used a regularity there. And now if you want to show that PC is less than or equal to d minus 1 for a regular tree, you use something known as the second moment method, and using the second moment method you want to put a lower bound on this. So for this inequality we gave a upper bound on this. Was the first step. The second step will be to give a lower bound on the same probability. So using this lower bound you can show that PC will be less than or equal to d minus 1, and this lower bound will be achieved using the second moment method, and the upper bound will just the first moment method. So using these methods you can prove that PC of TD is equal to d minus 1. So I don't want to do this computation. It's a very elementary computation, but it's just not necessary right now. So I'll just say what the lower bound is now. Lower bound. So you can use this bound to show that PC will be less than or equal to d minus 1. So this shows that PC of TD will be equal to d minus 1. So what about PU? Well, PU is just PU of a deregulatory is always 1, and this is sort of it's hard to prove, but it's very easy to see. Like if you have a deregular tree like this, and if you have some value of p where there's a unique cluster, well then just breaking off the edge, just breaking off one edge will give you two infinite clusters now. So pu of a tree will be equal to one, because there's no way that two infinite clusters are connected to each other except just by one edge. Simply removing that one edge will give you pu is equal to one. So for trees we know that the value of pc and the value of pu. So pc is never equal to pu. So that answers the first question, that for a deregular tree pc and pu will not be the same. And the second question also, that we know the value of pc and pu. So now finally this is the most interesting question, that what is this? So this is 0. So there is continuity for trees, for deregular trees. And the argument there is very simple. Basically, what happens is that if you have a deregular tree, then percolation on this deregular tree will exactly just be a Galton-Watson process with offspring distribution binomial d minus 1 into p. Sorry, binomial d minus 1 into comma. And then there is a theorem in Galton-Watson theory, is that extension happens also for when the mean is equal to 1. Since extension happens also when the mean is equal to 1, it also happens when p is equal to 1 over d minus 1. So which is exactly what we wanted to prove, that it will go extent also where when p is equal to d minus 1. So just using this Galton-Watson process, you can say that continuity is also holds for trees. So we know all these answers for trees. So the next step is that if you know it for trees, what about lattices and population on ZD? So for ZD, like I said, we know the first question, that yes, PC equal to PU, and so the second question is sort of hopeless. I don't know the answer. No one knows the answer of what PC of ZD is. We know that it's between this and this, but that's the best that we can do. And PU is even more known. But there is one thing that we can show, that theta of ZD is equal to 0, and not for all D. So this has just been shown for D bigger than equal to 7 or D less than equal to 2. So the middle 3, 4, 5, 6 is left, but for ZD for bigger than 7 and less than 2, we know continuity. Okay. By the way, this is a conjecture for amenable graphs. And this is conjectured for all graphs, so for all transitive graphs. So for all transitive graphs, we have conjectured that theta of PC will be equal to 0. So for ZD and for trees, more or less, we sort of have some sort of a command over the problem, but after that, it just gets crazy and we don't really know much stuff. So, but I'm going to show some things about ZD. Firstly, let's talk about the number of infinite clusters. So the number of infinite clusters is a random variable. Okay, so let's denote this random variable an infinity, and in theory, it can take values in 0, 1. So it can, this random variable, so n infinity of omega for a particular configuration will take values in this set. So then there is this theorem by that I just talked about. I don't know if the spelling is two n's or one n. So yes. So n infinity is a constant almost surely, and it belongs to 0, 1 and infinity. So why is n infinity a constant? Because so Bernoulli, we're doing Bernoulli percolation, so we're just tossing a coin for each edge, and so n infinity is a constant because it's something known as an invariant event, and for invariant events the probability of it being a constant is 1. So just sort of take that as, so n infinity will be a constant k almost surely. Let's say that this k, the second part, belongs to 2 3 like this. So then what happens? So if this k belongs to 2 3, so there are more than 2 clusters and less than infinity, then you can with positive probability find 2 vertices x and y which are in different clusters. Now in the original graph they were connected, so they were connected by some path. You just simply add back the path, and so with positive probability, I mean this is also some argument that if you add back the path, then this event will also have positive probability. So basically what I'm trying to show is that if uh, the event that you have 2 clusters has a positive probability, and when you add back this path, this event also has positive probability. So both events have positive probabilities, but the n infinity is different in both of them. But this contradicts that n infinity must be a constant. So n infinity can only take values in 0, 1 and infinity, because you cannot do such an argument for those cases. Yeah. So right, and then was this theorem by Burton and Keene. For all lattice-like graphs, PC is equal to PO. Okay. So this is basically the classical theory that I explained, and we have all these problems. So these are the 3 main problems. This is a conjecture, and that is a conjecture, and this conjecture was solved in the hyperbolic case very recently. It's a big 40-page proof, but it's a very nice proof. Uses all techniques from hyperbolic geometry and to prove it. But one thing that I would want to say is that there is no particular direction to prove it in generality, because if you read the proof for the hyperbolic case, it's very specific towards the hyperbolic nature of the graph. So there's no way to extend it, and so this conjecture, the first one, is still sort of left for a large class of graphs. Okay. So now comes the main point of the talk that I wanted to talk about, and it's a very simple proof. So I'll just say the theorem here. So this is what I wanted to show. So first I'm going to write the conjecture. Okay. So let me write it. So the conjecture is, it's conjecture 4 in their Benjamin Ishaan paper. So this is Benjamin Ishaan conjecture 4, and the conjecture is that so critical percolation dies in every transitive graph provided PC is less than 1. So this condition is important. I mean, obviously, because if PC is equal to 1, then it cannot die. I mean, everything is there. So critical percolation dies for all graphs where dies just means that theta of PC is 0. So dies at P. This means that theta of P is equal to 0. So this is a conjecture. And so there is this very simple proof by Ashcroft proving this for all graphs with exponential growth. So that's a big class of graphs. So I'll just right. Um, theorem is that actually let's just deal with only transitive graphs and it doesn't matter. So almost surely this random variable is 0 at PC. So the number of infinite so you this notation I haven't explained. This notation just means that g of p is that graph that you're left with. So when you're doing percolation with parameter p, g of p is the random subgraph of is that random subgraph. So what I want to show is that at PC the number of infinite clusters is 0. So we understand the theorem, right? So this is the main theorem that I want to prove, and then I'll be done. So by the way, before we go forward, there is this very important corollary. This is Russ-Lyon's theorem, and the theorem is that uh, if we have a transitive graph with exponential growth, then PC has to be less than 1. So classical proof of this uses some very high techniques, sci-fi techniques, like you construct a lexicographic tree and you show some coupling, and then PC will be less than 1. But this theorem completely kills this theorem, because if PC were 1, then this certainly could not happen. So it's the immediate corollary of the theorem. So to prove this theorem, the proof of the first theorem, even though it's very recent, it is a very simple proof, and it requires only two lemmas. And one of them is from analysis, and another one is a classic theorem in probability. So, so I'm just going to do that. Okay, there are three theorems. I'm sorry. Yeah. So first, I want to define the notion of a increasing event and a very important inequality there. So, okay. So an event A is increasing if omega less than eta and omega in A implies that eta is in A. So basically, if you have some random subgraph and you're just adding more edges, that will still be in A. So that's an increasing event. And so, what are the examples of increasing events? So something like x connected to y. This is an increasing event, right? Because if you add more edges, they still stay connected. Something like x infinity, even these two are increasing events. So it's very obvious to see these are increasing events. So then there is this very important inequality called Harris's FKG inequality. You can simply just say Harris's inequality and just says that if for increasing events A and B. So what this is saying is that the increasing events, if you take two increasing events, they are positively correlated. Okay, and equality holds if and only if they are independent. If these two events are independent, then only the equality will hold. So this is Harris's inequality. I will not be proving it. It requires very good techniques from martingale theory and stuff like that to show this, but so it's a good proof actually. Okay. So this is one machinery that we will require. The other one is something known as Feket's lemma. So I will state a version that is going to be convenient to us, and we're going to just work with that. Okay. So yeah. So let's say that let's number them 1 and so I'm going to write it. If we have a positive sequence of real numbers and am plus n bigger than am times an, and an is less than equal to c times mu n, then so if we have this sort of a super multiplicative sequence, then and we have this upper bound for these terms, then we can remove this constant c. It's a very powerful lemma that you can remove such a constant c, and this essentially just follows from Feket's lemma. So follows from Feket's lemma. Feket's lemma essentially just says that an will be less than equal to the limit of am to the power 1 by m whole to the power m. So using that, you can just say that will be c to the power 1 by n, and then you can get rid of c as n goes to infinity. Okay. So this will be very important. Finally, the classical theorem that I really love is theorem by Eisenman and Barsky. And so the theorem is that since it's a transitive graph, it doesn't depend on the vertex. Oh, you're saying that the expected size of the cluster of the origin, you let that be chi p. The theorem is that chi p is less than infinity for p less than pc. And so yeah, this is a involved proof, and the classical proof is very hard, but Hugo and others, they gave a very easy and simple proof for this. In fact, they showed that. So this is not really needed. So I'm 3 prime. Uh, let's just say HTC or something, and they showed that chi p, so that's infinity if and only if p is less than pc. So we won't be using 3 prime, but still. Okay, so that's all that we need. So it's very surprising that we just need these two elementary inequalities and this one result to show the this theorem. Okay. So first, let me define what I mean by a graph which has exponential growth, and then we'll move forward. So the exponential growth rate, is defined as so you can. So this is the growth rate. You just fix the origin. You look at the size of the ball of radius r to the power 1 by r, and this is grg. And graph is said to have exponential growth if the growth rate is strictly bigger than 1. So this is what I mean by a graph with exponential growth. All right. So I cannot rub this, rub that. Okay. Uh, all right. So yeah. So let's just start with the proof. So n infinity of GPC, what can it be? By Newman and Sherman, we know that it can only be 0, 1 or infinity, right? Suppose it's not 0, then it can be only 1 or infinity. So then we do it into two different cases. Case 1 is when G is amenable. So if G is amenable, then this n this is should be infinity, right? So if G is amenable, then n infinity cannot be infinity by Burton-Keen. So if G is amenable, then n infinity of G of PC has to be equal to 1, right? And so I cannot write here, right? Can I? Okay. Um, so if G is non-amenable, then we have two subcases. So don't, I mean, these are just words. If you just understand the surface grammar, it's going to make sense. So let's say case 2.1, G is a group. Uh, in case 2.2, G is not a group. So these are the two cases, and so I'm going to say some big theorems now. So there is this very big theorem by Benjamini, Lyons, Perez, and Schramm that says that for a non-amenable group, theta of PC will be 0. So using, I'm just going to say BLPS. This tells us that we are done. So in the case of a non-amenable group, there is this very classical theorem by Benjamini and BLPS that says that we are done. And in the other case, when G is not a group, there is a theorem by Timar that says that an infinity can only be one, it cannot be infinity. So for a non-amenable graph which is not a group, an infinity cannot be infinity. So if you look at, even if you don't understand, it's actually this, I replace the word unimodular with a group and non-unimodular with not a group, but just not to confuse you. And it's like, if you just understand the words, then to prove the theorem, we just need to show that an infinity cannot be one, because these three cases will tell us that an infinity cannot be infinity, right? This case tells us that cannot be infinity here, cannot be infinity here because it has to be 0 here, and it cannot be infinity here. So all we need to prove is the following. So what can I rub? I can write there as well. Okay. So what we have shown is that this theorem. So for a transitive graph, this is what we have shown, that it cannot be infinity. Okay. So let's name that theorem. I'm just going to say star. So to prove star, it suffices to show so we will assume that at criticality such graphs have unique cluster, and then we'll get a contradiction. So that makes sense, right? So we'll just show that an infinity of GOPC cannot be 1, and so that will do it. So yeah, now we have to just show that. Okay. So first I'll say lemma 1, whatever. Actually, before lemma 1, let me define something. So this kappa p of n is basically the infimum of the 2-point function. So I'm taking this a probability that x and y are connected, and I'm taking the infimum over all xy such that the distance is less than or equal to n, and this is what I'm calling kappa p of n. So it might seem like a weird definition, but so this lemma to sort of motivate why we are defining such a thing. We just want to show something like this, that kappa pc of n will be less than or equal to the growth rate of g to the power minus n. So this will prove the theorem. And so why will this prove the theorem? Because since the growth rate is bigger than or equal to 1 for graphs with exponential growth, if you take the limit as n goes to infinity, this goes to 0. But this is always bounded above by something. So probability if you assume a unique infinite cluster, then this 2-point function is bounded by this greater than or equal to c square, and the probability that x will be in that infinite cluster is positive, and this is also positive. By transitivity, these two probabilities are the same, and so for any x and y, this will be bigger than or equal to some positive constant. But here we'll be showing that it's less than or equal to 0, so that will be a contradiction. So there cannot be a unique infinite cluster. So if you prove this lemma, then we'll be done, right? Okay. So this is just Harris's FKG inequality. Here your A and B are so this is A and this is B, and so the probability of A intersection B is greater than or equal to these two probabilities. Okay. So I don't want to rub the theorem. So this is just, I just want to write by 1. This 1 was here. Okay. So now we're almost done. The first thing is that kappa p of n is super multiplicative. So why is that? So imagine you have two vertices u and v such that the distance between them is less than or equal to m plus n. So all we want to show is that kappa p of m plus n right, this is what we want to show. So if you have two vertices u and v such that the distance is less than or equal to m plus n, you can always find a vertex in middle such that this distance is less than or equal to m and this distance is less than or equal to n. Then again, by Harris's inequality, you can say that the probability that u and v are connected is less than or equal to the probability, greater than or equal to the probability that u and w are connected and w and v are connected. Now if you take infimum on both sides, you will sort of get this inequality. Have I reversed it? Right, yes, I have reversed it. If you take infimums, you will get this inequality, right? So kappa p of n is super multiplicative, and now I'll just give a bound on it, and that will be okay. So now we'll use the where is it? Yeah, we want to use this. So we want to give a bound on kappa p of n, which looks like c times mu to the n. And so what we can say is that what is chi p? Chi p let's say what PC you are working with. So by 3 prime, we know that chi PC will be less than infinity. And chi PC is just this simply because you can write the random variable size of k naught as a sum of indicators that x and y are connected, and then taking expectations on both sides, you'll get this. So chi of PC is this, which is less than infinity. And so if I'm using the strict here, if P is less than PC, I'm just fixing any point in the vertex set and Bx comma n is Bn. And now I'm looking at this size. This will be bounded by this number, right? Kappa Pn is the infimum, so it will be bounded by this number. This is I should be okay. It's bounded by all these connection probabilities, and we're summing over Bn of them. So this gives us that, and okay. Fine. Let's just remove this. So now what happens is that we've shown that Bn times kappa Pn is less than the summation of is less than equal to pi p, right? Because I'm just summing over more things. So this is for all n. This is less than equal to this thing. So therefore, this thing is less than equal to infinity, and we get something like kappa p of n is less than equal to chi p uh, times is less than equal to chi p okay. So now here our constant c is just going to be chi p, and this is just growth rate to the power minus n. So this will immediately imply that kappa p of n is less than equal to right. So this is just because of this by 2. So we've bounded this by some finite. This is a finite constant like this c, and this is mu to the n, where mu is equal to this. So then we can do such a thing. So we have shown it for p less than equal to pc that kappa p will be less than equal to that. In fact, at pc also you can use the left continuity of the function to show that chi pc will also be less than equal to growth rate of g to the power minus n. So by some quantity arguments, you can show that chi pc of n is also less than equal to growth rate of g to the power minus n. And if you don't want to use quantity arguments, you can just use this theorem, and you can just replace p by pc and still work with it. So this shows that the chi pc of n is less than equal to the growth rate to the power minus n, which is what we wanted to show, because as soon as we have this, we can just take n to infinity, and we'll have that this limit goes to 0. But if this limit goes to 0, then well, it's also bounded by something positive, so that cannot happen, and so that's a contradiction. And so this is the proof for the graph with exponential growth. It's a simple proof in the sense that, I mean, if you look at the theorem from very recent years, and you won't expect such a like a 3-4 page proof, but this is the proof for graphs with exponential growth. So for linear growth, we know that it cannot happen because then PC will be 1. For exponential growth, that we know that the conjecture is true by this theorem. So only graphs which are left are graphs which have intermediate growth, and so that's still not solved. So we don't know the answer about the graphs with intermediate growth. Intermediate growth just means that it's not greater than 1, the growth rate. But intermediate growth, you define it some other way. You don't use the exponential growth rate, but yeah. So that's basically what I wanted to talk about, and yeah, that's it.
So let's thank the speaker once. Any other questions? Yeah. Oh, yes, sorry.
So can we replace this idea of transitivity by something, let's say, slightly weaker?
Yeah, we can. So you can, yeah, I should have said that all these theorems only work for transitive case, but you can replace the word transitive by quasi-transitive. Just means that if you're looking at the action of the automorphism group of G, there are finitely many orbits. So the transitive case there is only one orbit. For quasi-transitive, there are finitely many orbits, and you can still do it. Is that what you wanted to ask?
Thank you.
And these constants also you can improve somewhere, but it's sort of inefficient, but works. So.
So, no other questions? I think you should mention some references for the thing.
Right. So those were in my slides. So I'll just send the slides.
Okay, yeah. We'll upload the slides on the MathClub page then. Okay, if there are no other questions, let's thank the speaker once again.
Thank you.
Okay, thank you.